Hello and welcome to this video lesson on monitoring reactions. It has specification reference 3.1.9.2 and there's only one lesson objective in today's video, and that is how do we measure the rate of reaction using a continuous monitoring method. And the first thing to establish is rate of reaction units. So before you were familiar with the units, for example centimeters cubed per second or grams per second, changing grams per second as a measure of measuring the rate of a reaction. But at year 13 we get more into changing concentration per second. As you know, the units of concentration are moles per dm cubed, and so the rate of change of concentration would be moles per dm cubed per second. So that's how we measure the rate of reaction from now on. And a continuous monitoring method, that is just a method where you take regular readings throughout the reaction. So the reaction might start and every 10 seconds you might take a reading. It might be a volume of gas, it might be a mass, and you track that over time, and then you can convert that into your reaction rates later. But a continuous monitoring method just means that you're taking regular readings of data over the course of the reaction. Now what we're going to do is we're going to consider all the ways, and there's 4 ways of measuring progress of a reaction by continuous monitoring. And so the first one is by measuring the change in gas volume. Right, so we're going to measure the change in gas volume. And so this reaction, for example, might be your calcium carbonate with your hydrochloric acid, and then you're going to get a gas given off. In this case it would be carbon dioxide. And what you do is you track, carbon dioxide goes up here and into the measuring cylinder, and what you do is you just track the amount of gas, carbon dioxide, that's being given off over time. And so that would be a gas volume way of measuring the progress of a reaction. That would be method number 1. Method number 2 we can look at is to measure the change in a pH. So here we've got a pH monitor. So the sample would be the blue solution here, and the pH monitor is the probe that's going into the solution, and your pH reading is coming up on this screen there. And as time goes by, you would just note down what the pH is, and that would give you your readings over time of pH. Of course, it has to be a reaction where hydrogen ions are either being created or destroyed, such that the pH will change. But for those reactions, this is a good way of measuring the progress. So we'll just call those the pH change way of measuring the progress of a reaction. And thirdly, what we can do is we can measure the change in colour of the reaction mixture if it changes in colour. So for example, if you've got a reaction that involves iodine, which might be brown coloured in solution, and the reaction uses up the iodine, the brown colour would gradually disappear, and the reaction mixture would become colourless as the iodine disappears. And so you could use a gadget called a colorimeter, and this is our colorimeter here that the student is using, and he's got a sample. The sample is here, and the colorimeter is just measuring the amount of light that goes through that solution. So as it becomes clearer, more light goes through, and that's what he records. And he records the absorbency, the amount of light that's been absorbed, over time, and you notice here he's got a stop clock to record the readings at various time intervals. Okay, so how do you get concentration from that though? Well, you need to also create a calibration curve. So what you might do is you might make up some standard solutions at certain concentrations. So let's say you make up 1, 2, 3, 4, 5 standard solutions that you know the concentration of. You put those in your colorimeter and you find out that the absorbency readings come out such as this. You plot your curve, and then what you might do is you might look at your unknown substance in your reaction, and at any point in time, let's say at a point in time the absorbency is 0.5. Right, so if the absorbency is 0.5, then you know that the concentration is about 6.2. And if at a different point in time, if the absorbance was 1.0, then you'd be able to read off your calibration curve that your concentration would be about 8.2, etc. And so that's what we call the color change method. Using a colorimeter, that's the color change method for measuring the progress of a reaction where we get a color change. So that's 3 methods. The last method is this one here, where we measure the mass. So it might be actually the same reaction that we had in the first example with calcium carbonate and hydrochloric acid, and the mass is going to change because you've got a gas coming off. And as the gas comes off, the mass of the flask and the reaction mixture decreases, and you measure that decrease, and you take readings at several points in time to get your progress over the reaction until there's no change, at which time you know that the reaction has finished. So this last method is called our loss of mass. Our loss of mass method, and there we have 4 methods of measuring the progress of a reaction depending on the reaction, and they're all continuous monitoring methods. So what we're going to do next is we're going to have a look at 2 of these methods in a bit more detail. Firstly, we're going to have a look at the gas volume method, and we're going to see how we get from these measurements of a volume of a gas over time to a reaction rate changing. And secondly, we're going to have a look at the mass loss method in the same way, and we're going to get a little bit mathematical about it too. So here we have a exam question to give us a structure to work with, and as you can read, a scientist is following the reaction between 500 cm cubed of 2 mol per dm cubed hydrochloric acid and 25 grams of solid sodium carbonate. So they're going to react, and you're going to get carbon dioxide coming off. And the experimenter is monitoring the volume of gas produced at room temperature and pressure. And she takes her measurements at 15-second intervals, and her results are recorded in this table. And what we want to do is we want to calculate the concentration of hydrochloric acid at each time point. The time points being 0 seconds, 15, 30, 45, 60 and 75, of course. So we want to go from the volume of gas to concentration of hydrochloric acid, because then what we can do is we can plot the change of plot the concentration of hydrochloric acid against time, and therefore from the gradient get the change in concentration of hydrochloric acid at any particular point in time, and that will be our reaction rate at a particular point in time. So let's start off and just have a look at this part of the question here where it mentions room temperature and pressure. And so when we consider the units of room temperature and pressure, the pressure bit is going to be 100 kilopascals, and we know that the temperature in Kelvin is going to be 298, and that's room temperature and pressure. So looking at the question, the first thing that we should probably do is we should write down the balanced equation. So the question tells us we've got some hydrochloric acid, and it's reacting with sodium carbonate, and you will notice that carbonate is a 2- ion, whereas sodium is a 1+ ion. So the formula of sodium carbonate is going to be Na2CO3, and that's going to make some sodium chloride. We're going to get some carbon dioxide given off, and it's a neutralization reaction, so we're going to get some water as well. Okay, let's just make sure we're all balanced. I think to balance it we need a 2 here, and therefore we need a 2 here, and after that we're all balanced. So that's our reaction, and it will become clear why we need that balanced equation in due course. So let's just plan out what we're going to do. What you see is that we have we've got volume, but actually what we want is we want concentration, and our units for concentration of course are moles per TM cubed. So we're going to need to go from volume to moles, so that we can find our concentration, and that should set off the ideal gas equation in your mind. And let's just try and remember that our ideal gas is PV equals nRT. That's our ideal gas equation, and what we can do is we can rearrange that, because what we want is moles. All right, so the moles is going to be N is going to be PV over RT, where the volume and the moles are going to be referring to our carbon dioxide, of course. So our carbon dioxide is coming off, we've got the volume of that, we want the moles of carbon dioxide, and we're going to use this rearrangement of the ideal gas equation to give us that data. So what we can do is we can add a row to our table, so we could say moles of carbon dioxide here, and that's going to be 0, of course. So what we're going to do is we're going to work out the moles of carbon dioxide at 15 seconds. So I'll just switch colours just to make it a little bit clearer. So our moles at 15 seconds is going to be the pressure, which is 100. Now, units, be careful of units. We've got 100 kilopascals given up there, but the units in the ideal gas are pascals, so we need 100,000 of those. And our volume is 140 cm cubed, but the units in the ideal gas is meters cubed, so we want 140 times 10 to the minus 6, divided by R. R, you'll remember, and if an exam you'd be given this, but you probably remember there's 8.31, and our temperature is already in Kelvin, and that's 298, and so we just plug those into our calculator, and I think what we do is we get 5.65 times 10 to the minus 3 moles. So we could write that in here. So we've got moles of carbon dioxide, but looking back at the question, we want concentration of hydrogen of hydrochloric acid. And so what we have to do is we have to convert our moles of carbon dioxide into moles of hydrochloric acid. that's the little calculation we want to do there. And as usual, what we want to do is we want to refer back to the balanced equation here. So from the balanced equation, we can see that for every 1 mole of carbon dioxide that is made, we would use up 2 moles of hydrochloric acid. In this case, we have made so far 5.65 times 10 to the minus 3 moles of carbon dioxide. So we must have used up twice that. So we must have used up twice that. So 5.65 times 10 to the minus 3 times 2 is the moles of hydrochloric acid used up, and that equals 11.3 times 10 to the minus 3 moles. But that's not the number we want yet. That's the amount of hydrochloric acid that's been used up. We want the amount of hydrochloric acid that remains. And so what we have to do is we have to look at this data here, because that is telling us what we started out with. So this tells us that there was 1 mole of hydrochloric acid in the reaction mixture to start with. We've used up 11.3 times 10 to the minus 3 moles in the first 15 seconds. And so this number, the number of moles that we're interested in, is 1 take 11.3 times 10 to the minus 3. And that equals 0.988 moles. And what we would do is we would do that for here and here and here and here. Exactly the same calculation. You might try that on your own if you like. But for the sake of time, what we're going to do is we're going to carry on to get the answer, at least for 1 time point. So we have moles of hydrochloric acid, but we want concentration of hydrochloric acid at each time point. And so that's what we have to do. We have to convert our moles into concentration. And so what we have to do is just divide it by the amount of volume that we have. So we've got 0.988 moles divided by the volume, and the volume is 500 cm cubed from the question. But of course, dm cubed is the units of concentration, so we have to convert that 500 into dm cubed by dividing it by 1000, and so that would equal 1.98 moles per dm cubed. And that is the concentration of hydrochloric acid that we've been asked for. It's the concentration of hydrochloric acid at the first time point, 15 seconds. And so what you would do is you would do that same process for each of the time points in order to get the full answer. But that's where I'm going to pause for now, and we're going to look at a slightly different example instead of completing this one. And here's our second example. It's a mass loss example. Here, let's read it. A student places 5.2 grams of zinc in a conical flask containing 225 cm cubed of 1 mole per dm cubed hydrochloric acid. So the initial mass of the reaction vessel and all its contents is 389 grams, and he monitors the loss in mass of the container over the course of a minute. And his results are in the table below. And just as before, we need to calculate the concentration of HCl at each time point. this one, this one, this one, etc. So a concentration of HCl, but we have just got the mass of the reaction vessel. So look, this is chemistry, so it's always a good idea to start off with the balanced equation. And so we've got some hydrochloric acid, and we've got some zinc, and we're going to make some zinc chloride and some hydrogen gas. And that's balanced already. So the mass lost is going to be the hydrogen gas that is going to escape into the room. And as it does so, it leaves less mass in the conical flask and reaction mixture. So that is the mass lost. But we don't have mass loss in our table yet. We have the mass of the reaction vessel. So let's add another row, calling it mass lost in grams, and the mass loss is just going to be the 389 grams that you started with minus what you have after a particular amount of time. So at 10 seconds we started off with 389.00, take 388.97, so we have lost 0.03 grams after 10 seconds. And you could do the same for each of the time points up to 60 seconds. So now we've got mass lost. And as we said before, that mass lost is the amount of hydrogen that has escaped. So why don't we work out the number of moles of hydrogen that has escaped. So moles of hydrogen escaped, so 0. And so what we're going to do is we're going to use moles equals mass over AR or MR to find our moles. So mass is 0.03 grams, and our MR of hydrogen gas is going to be 2 times 1 is 2. So our moles is going to be 0.015 moles of hydrogen gas that's escaped. Okay, so next step is to go back to the balanced equation and notice that for every 1 mole of hydrogen gas we use up 2 moles of hydrochloric acid. So if we had 0.015 moles of hydrogen gas being made, we would use up 0.03 moles of hydrochloric acid. So let's write that down. Moles of hydrochloric acid used up, which is not useful to us yet. So that is used up. So we can say here that we have 0.015 times 2 equals 0.03 moles of hydrochloric acid has been used up. But we want what is left. So here we can write moles of hydrochloric acid left. And for that we need to look back at the question and remember that we've got 225 cm cubed of 1 mole per dm cubed hydrochloric acid. So we're going to use concentration equals moles over volume, and we're going to rearrange that to moles equals concentration times volume. So our moles that we started off with is concentration, which is 1.0 from the question, times volume, which is 225, but notice it's cm cubed, all right, and we want dm cubed, so we have to just divide that by 1000. So our moles turns out to be 0.225 moles. So we can write that in here, 0.225. That's the amount of hydrochloric acid that we started with. And to get the moles of hydrochloric acid that's left, we're going to start with our 0.225 and subtract that. From that, what we have used up, which was our 0.03, and so that leaves us with 0.195 moles of hydrochloric acid that's left. But we want concentration. The last step is to work out concentration, because the question here is asking us for concentration at each time point, and we're going to use this same equation here. So concentration is our moles over volume, so concentration is going to be moles, which is 0.195, and our volume is still our 225. Alright, but convert it into dm cubed. So our concentration after 10 seconds is 0.195 divided by 225 over 1,000, and that comes out at 0.87 moles per dm cubed. And that is the answer that we could put in here in our bottom column. So our concentration in square brackets of hydrochloric acid after 10 seconds would be 0.87, and our units of course are moles per dm cubed. And that is what we've been asked to do, at least for one time point, and you would just do the same for all the other time points, and then you would have the answer to the full answer to the question. And if you did do that for all of the other data points, you would have 1, 2, 3, 4, 5, 6, 7 values of concentration of hydrochloric acid at 7 different points of time. And so then you could plot a concentration versus time. So that would be the concentration of hydrochloric acid over time. So it would start quite high, and as the hydrochloric acid is used up in the reaction, it would decrease. It would decrease quite quickly to start with, and then as the reaction's finished, it would plateau off. And so you get a curve something like that, assuming that hydrochloric acid is in excess and you've used up all your zinc by the time the curve goes flat. And so then what you would do is you would work out the rate. Say you wanted the rate at T1, then you would take this point of the graph and you would draw a tangent. Right? So you would draw the tangent at that point, and then you would work out the gradient of that tangent, and that tangent would, the gradient of the tangent would give you the rate. So the gradient gives you the rate at T1. But that graphing business is the subject of a whole lesson, and so we'll deal with that in more detail in due course. So that's it for this video lesson on monitoring reactions. How do we measure the rate of reaction using continuous monitoring methods? Well, we looked at 4 different methods, and we did a couple of calculations as well, going from the data that we recorded to the concentration of a reactant, from which we could then work out a rate of reaction if we wanted to. We didn't go into that in a lot of detail. That's the subject of another lesson. Okay, I hope that's been clear.